Alrighty, hi guys. So today we're going to be learning about specific heat. And so specific heat is another property of matter, which is why we're going to be talking about it here. Just like density is a property of matter, specific heat is a property of matter. It's inherent to an object or a piece of matter, and doesn't change whether you've got a big piece of it or a little piece of it. So like the density of water, regardless of whether or not you have 100 mils of water or 10 mils of water, is still 1 gram per mil. And the same thing goes for specific heat. Regardless of how much of that matter that you have, it is the same. It's an inherent property. It's a physical property. So let's talk about that. So specific heat is specifically the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And so that's what it is. It's the amount of heat required, and we use kind of heat and energy interchangeably here, but it's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And we can calculate specific heat, and it's utilized in the equation Q equals mc delta T, where Q is the heat, M is mass, delta T is change in temperature. Anytime we're talking about a change in, we use the Greek symbol delta. That means change in temperature, which would be the same as T final minus T initial, the change in temperature. And then C being our specific heat. Okay, so that's going to be an important equation that we're going to learn. Q equals mc delta T, or as I sometimes call it, sorry about the bell guys, as I sometimes call it, Q equals mcat, because it kind of looks like the word cat. So specific heat can be referred to as a measure of thermal inertia, where inertia describes how easily something can accelerate, and the lower the inertia, the easier it is to accelerate. So something with a higher mass has a higher inertia and is therefore more likely to keep going and not accelerate or decelerate. So when we're talking about thermal inertia, then we're talking about the ability to increase or decrease a temperature. So thermal inertia describes how easily something changes its temperature instead of its acceleration. Something with a high specific heat is more likely to stay at the same temperature. So if something has a high specific heat, you have to put a lot of energy in order to get it to increase in temperature. Something with a low specific heat is the opposite. Low specific heat means you don't have to put a lot of energy in to get it to change its temperature. So on a pizza, there's the crust and the cheese and the sauce. And right after it's taken out of the oven, what has the higher specific heat? The crust or the cheese and the sauce? So if you think about taking a pizza out of the oven, the part that burns your mouth is definitely the cheese and sauce, right? So which one then has the higher specific heat? The crust or the cheese and the sauce? So think about that for a second. And if you think about it, if a high specific heat means that you don't change the temperature very much, which part of the pizza doesn't change its temperature as much? That would be the crust, right? So because the cheese and the sauce, we put it in the oven at the same energy, right? But the cheese and the sauce got a lot hotter than the crust. So the same amount of energy being input caused a greater change in temperature, which means is that it has a lower specific heat because less energy was required to get a change in temperature. Also, you can think of it alternatively, the cheese and sauce tends to cool off a lot quicker than the crust. And so the crust, since it's more likely to stay at the same temperature or heat, the crust would have a higher specific heat than the cheese and sauce. So that's just kind of a theoretical thing to think about. All right, so specific heat is measured in units, and they are called joules per gram degree Celsius or calories per gram degree Celsius. And that's all to do with the way that we calculate it, and we'll talk about that in a second. But the relationship between these two is the fact that 1 calorie is equal to 4.18 joules. So whichever one we use, I prefer to use joules per gram degree Celsius. Calories is more of a biology thing, but I use joules, but you can relate them back and forth through 1 calorie is equal to 4.18 joules. So Q is heat, the energy transferred between two objects, one hot, one cold, due to the difference in temperature. Joules or calories are the units on it. Mass is the mass of the substance, it's in grams. C, the specific heat, is the energy it takes to increase 1 gram of a substance by 1 degree Celsius, and it's measured in joules per gram degree Celsius. And then change in temperature, the final temperature minus the initial temperature, usually in degrees Celsius. Okay, so that's just kind of restating what we've already talked about. Now I'm going to go through an example problem. So how much heat is required to raise 100 grams of water from 50 degrees Celsius to 70 degrees Celsius when the specific heat of water is 4.18 joules per gram degree Celsius? So we're going to have to use that Q equals MC delta T equation. But let's figure out what our things are. What is, and I want it to, oh, it went away. Okay. So what is my mass? Because we're trying to find how much heat. So we're trying to find Q. So we're solving for Q. So my mass should be that 100 grams of water. My C, or specific heat, is 4.18 joules per gram degree Celsius. And then my delta T is going to be 70 degrees Celsius minus 50 degrees Celsius. So 100 grams times 4.18 joules per gram degree Celsius times 70 degrees Celsius minus 50 degrees Celsius. Now, the answer, if we multiply all this in our calculator and if you look at the units, everything's going to cancel out. These grams on top cancel out with these grams on bottom. The degrees Celsius on top cancels out with the degrees Celsius on bottom, leaving us with joules. And if you type that all into your calculator, 100 times 4.18 times 70 minus 50, you're going to get 8,360 joules. Now, that is technically not the correct answer with sig figs, but I just wanted you to see that for this, because my question only technically has 1 sig fig, so the answer should have been 8,000 joules, but I want you to see the actual answer. Now, I want an example for you to do. So go ahead and look at this. How much heat is required to raise 100 times, or 1.00 times 10 to the 2 grams of aluminum from 50 degrees Celsius to 70 degrees Celsius when the specific heat of aluminum is 0.900 joules per gram degree Celsius? So take some time and work this out. Try plugging it into the equation. Should just be a plug and chug. And then pause the video and come back to me and we'll go through it together. So again, we're looking at heat. So we're looking for Q equals MC delta T. We're solving for heat. We've got mass, 1.00 times 10 to the 2 grams. We've got C at 0.9 joules per gram degree Celsius. And then we've got our delta T, 70 degrees minus 50 degrees. So if we plug that in, we get 1.00 times 10 to the 2 grams times 0.900 joules per gram degree Celsius times 70 minus 50, and you're going to get 1,800 joules, okay, or 1,800 joules. So we're going to go through more of these problems, and we're going to go through problems where you're going to have to solve for C or M or delta T tomorrow. But come to me, tell me what the important things that you learned are. So think about what the things you learned today are, and we're going to go through those tomorrow. I will see you tomorrow. Or actually, it's probably going to be later. Bye.